So, in this video, we're going to be covering composition of functions. So, in particular, we're going to be talking about the notation that's involved. There's a couple different types of notation, and sort of how to tell when it's well-defined or when it makes sense. Okay, so as a starting point, the notation. So, there's two types of notation that we're going to be sort of going through, and they're easiest to see sort of by example. So, just picking sort of functions out of a hat, let's say we have these two functions here, right? So we have this f of x, right, the 3x squared plus 1, and the g of x, which is that natural log of 3x minus 2 to the x. So the particular functions here aren't the exact important parts, but we want to see how they interact. Okay, so the first type of notation we have for composition, that's this sort of unhelpful to say because they're all read this way, but f of g of x. But the idea here is that we can think of g of x as being sort of the input where x, right, was that dummy variable. So the f of x notation, remember, we have that dummy variable and then the rule sort of tells us what to do with it. Well, we could put anything in as that dummy variable, so we're going to put in this g of x, right? So we put it in just in place. So it was 3x squared plus 1, or 3 times the input squared plus 1. So same deal here, 3 times the input, which is now g of x squared plus 1. But g of x itself, right, has this other definition, right? It has its own rule. So then we can plug that in place of g of x, right? So this is one way we can compose the functions. Now, there's another type of notation that is, again, just another type of notation, but it means the same thing. And that is this other way of doing f of g of x, where we have this sort of circle bit here. So this, right, if you see the parentheses here, the f and the g are in their own parentheses, and then that as a unit is being applied to x. But the output is sort of the same at the end of the day, okay? These are just notational differences. And in fact, personally, I find it easiest to go from this kind of notation to the sort of first type of notation as the first step, just to make it clear sort of what I'm doing with that. But I want to be sort of very clear here, draw your attention to the fact that that dot is not the same as the multiplication dot. So down here, right, we have the compose symbol, which is like an open circle, versus the closed dot, which is the product symbol. So open dot, that's the composition of those functions. The sort of closed dot, that's going to be the product of those functions, okay? All right, so this is the sort of introduction or this sort of idea for the notation, and I went through that first bit here, but it's sort of important to notice that there are different ways that you can compose, meaning that if we look at f of g of x, that's one thing, and g of f of x is, as it turns out, a whole other thing. So it's sort of very important to know which order you're doing this in, and this is different than we're used to, right? If we did like products, for example, we could switch the product without any like real trouble. And even if we're doing something like subtraction where the order matters, we could do like, you know, plus negative and then switch it around as long as we keep track of signs. Turns out that's not the case with composition. They can be sort of radically different depending on what order you do it in. So again, looking at a sort of example here, f of g of x, right? We saw this one before. We put the g of x in, and then we sort of used that as the rule. So we did that thing squared plus 1, and then we expanded out what g of x was, which was this 3 times natural log of 3x minus 2x, 2 to the x, right? And we got this expression, right? Now, if we did g of f of x, well, we would end up with something that I'm going to claim is radically different, although sort of looking at it, that might not be sort of obvious. But if we look at what happens, right, it's the same sort of idea. We would take the f of x and plug it in as the x in the g of x equation, right? So the g of x was that natural log of 3x minus 2 to the x. So instead, we're going to have this f of x bit, right? 3 times f of x minus 2 to the f of x, and then we plug in what f of x is, which is that 3x squared plus 1, and then minus, right, the same deal, this 2 to the 3x squared minus 1. My claim is that these are wildly different things, and sort of looking at the numbers, maybe that is obvious, maybe that isn't, but we can actually see that much more clearly if we look at the graphs. So not that we would expect you to be able to graph these things because they're quite crazy, but supplying the graph for you here, this is the f of g of x version. And if we look at the g of f of x version, we get something completely different, right? That's the takeaway here. Not to worry about sort of actually graphing these, because you probably wouldn't be able to graph these very nicely, but we can see by looking at the graphs these things are radically different functions. So we can tell then that the order sort of really makes a difference which one we're doing. So the other part we wanted to talk about is determining when this thing makes sense, right? When is a composition well defined? And this is the part that tends to be sort of easy to overlook, because a lot of, determining this part, a lot of knowing whether or not this thing makes sense doesn't come from the symbols, okay? So again, doing this with an actual example, let's say we have the following two sort of functions that are modeling something in particular. So we have this P of t. This gives our profit in dollars of some amount of them, like $10,000 or something, but in dollars at time t in months for some company. So this is just a standard profit equation, and we have this t squared minus 2t minus 3, okay? Now for another function, something seemingly completely unrelated, what if we had this B of D, which gives us the number of bricks you can buy, sort of assuming that you're buying them in bulk, if you have D number of dollars, okay? So again, sort of just a random sort of thing that we could create here, the B of D, and then we get this equation 4D minus 50. Now, on the one hand, these things are just sort of functions. We could compose them, right? So we could look at something like P of B of X, right? Which, again, these notations are the same, so meaning the same thing, right? So this P of B, that little open circle, really means I'm putting B of D in as the input of P. And if I do that, again, the sort of exact computation isn't the important part, but the takeaway here is that I could get a thing, right? I could get some output, this 16D squared minus 408D plus 2550. I get some sensible function at the end. I could do the same thing the other way around too, right? Like I could do B of P. As we said, the order is important, right? So I get something different, and I sort of chug through all of that arithmetic and stuff, and I get down to 4t squared minus 6t minus 62. So both of these things are sort of easily computable. But that doesn't tell us whether or not what we just did made any sense, right? So to do that, we want to back up and think about what is actually going on in these functions, right? So what does it mean to do something like P of B of D, right? Composing the P function with an input of B of D. Now, the input, right, the ultimate input, the thing that we're putting in sort of at the very beginning to get something out at the very end, that is D, okay? So that's the dollars. We're inputting dollars into this thing. The output is going to be the profit of the company, because P is the last thing to have happen, right? So P is giving out profit, and D represented dollars originally. Now, on the face of it, this seems to make sense. I put in something about money, I get out something about money. So like this seems kind of believable if all I do is look at the input and the output. Unfortunately, though, if we look at the middle, things go kind of awry, okay? So if we think about what B of D outputted, B of D, right, is the sort of inside equation. Its output was number of bricks you can buy, right? So that means that before I sort of try to apply P, I applied B to that amount of money, and I got some number of bricks. But remember that P takes in as an input time in months. And that doesn't really make sense, right? Because what I'm trying to do now is I applied that B function, and I got the number of bricks, and then I try to put that in as time in months, right? I'm trying to sort of substitute bricks you can buy in place of time in months, and those have nothing to do with each other. So this composition, even though sort of I could compute it all the way through and get some function, and the input and output variables seem related, this thing is totally nonsense because that middle piece doesn't line up at all, okay? Now, in contrast, thinking of B of P of T, right? So I'm putting in time. I'm getting out right after B is applied. It gives me information about the number of bricks I can buy. This seems at least significantly less related, right, than just putting in money and getting out profit. So time in months and bricks you can buy seems like a weird sort of transition. But that P part, right, when I look at the middle function like we did last time, P is giving as an output some profit amount after T months, right? It's giving out money as its output. And B, as an input, wants some amount of money, meaning that these things actually line up pretty well. So here, this B of P part actually does work. It makes sense, right? Because this composition is telling you essentially, even though it didn't sort of seem obvious initially, it's telling you how many bricks you can buy as that company using your profits after T months, right? And the sort of key part here is that the middle function bit lines up. That output of that inner thing lines up nicely with the input of the outer thing, okay? All right, so takeaways. First takeaway, we got sort of right at the beginning, order really matters, right? If we sort of change what order we're composing in, we get something radically different as a function. Like even if it were to make sense, it sort of could be something completely different. So we have to be very careful when we're dealing with the order of composition. The second thing, though, is that you can't always tell if the composition makes sense just sort of looking at it, right? You can compute it almost always. You can always sort of get a rule at the end, but that doesn't tell you if what you're looking at sort of makes any sense. It could be completely nonsensical, like in our example where we were trying to put in like number of bricks you can buy in place of, the amount of time that goes by, okay? So the key idea there then is that the range of that inner function, right, the output of the inner function has to sort of work with the domain. It has to be a subset of the domain of that outer function. So in our case with P of B of D, that didn't work because the output of the inner function was number of bricks and the input needed to be time in months. So that didn't work for us at all. But when we flipped it, right, when we were doing the B of P, P has as an output money, right, dollars, and B needed to take in an input of money, so that did end up working, okay? Now, as a note here, though, it can be very sort of difficult to actually get the range itself. So although what we care about is the range, it turns out that the range can be difficult to actually compute. So a lot of the times we'll use the codomain, because that's given as part of the definition of the function, as a sort of quick check. Because remember, the codomain is always going to sort of include the range. The range is a subset of the codomain. So if the codomains line up, you know already sort of immediately that the range is going to work. But if they don't line up, then you have to actually figure out what the range is, and that can be very challenging. So for the sake of right now, you don't have to worry about knowing sort of how to find an arbitrary range, right? You're not going to worry about being given a function and just knowing whether or not that range works. That's something that we will discuss sort of as we go through specific functions when and where we can. But you want to know sort of the idea of the composition, that it has to make sense and how you could sort of know whether or not it does make sense. Okay. All right, so what did we do? We discussed composition of functions, right? We have the two different notations, the open circle versus the parentheses version. And we talked about how to like compute the rule bit, right? And going through and getting some actual sort of computational representation of that function. But we also talked about how to know whether or not that thing made sense, right? So we needed to know whether or not that middle piece actually worked out, whether the output of the inner function sort of was a subset of the domain of the outer function, whether or not those types of things lined up, okay? So that is that.